Hello everyone, my name is Roger and I will present our work on improving intrinsic exploration by creating stationary objectives, published at ICLR 2024. This work has been done in collaboration with Joshua Romoff at Ubisoft La Forge Montreal and Professor Glen Berseth at Mille Quebec and Université de Montréal. In this work, we focus on the fundamental problem of exploration in reinforcement learning, and particularly in the framework of intrinsic objectives for exploration. This framework introduces auxiliary rewards which help guiding the agent's learning process towards broader objectives. The ultimate goal of a generally useful intrinsic reward is to improve learning across many environments and discover emergent behaviors. In this work, we study several intrinsic rewards of different nature, concretely count-based bonuses, pseudo-counts, and state entropy maximization. Computing each of these intrinsic rewards requires estimating different models with learned parameters. These models are updated as the agents collect more data, and hence intrinsic rewards are non-stationary. For example, when using the count-based rewards, RL agents receive different rewards at the same state if they visited at different points in time, as the state visitation frequencies necessary to compute the counts are updated online. This poses a hard problem for the RL agents, since it is hard to estimate the true value of each state, as these seem to change over time. Eventually, this can lead to learning the wrong policies. To alleviate this issue, we propose SOPHI, a framework which makes intrinsic rewards stationary. SOPHI allows the agents to observe the parameters which make rewards non-stationary. Following the previous example on count-based rewards, SOPHI augments the original states in the MDP with the forever changing state visitation frequencies. Without using SOPHI, optimizing non-stationary rewards induces partially observed MDPs, which solving requires non-Markovian properties like memory and continual adaptation. Importantly, there is no guarantee for an optimal Markovian policy to exist in a partially observed MDP. More generally, SOPHI is a two-phase process which requires first identifying the sufficient statistics of the intrinsic rewards, that is, the set of parameters that are updated online with the agent and cause the rewards to be non-stationary, and secondly, augmenting the agent states with these parameters to give as input through a deep network. Throughout our work, we find different representations for the sufficient statistics, depending on their corresponding intrinsic reward formulations. For instance, we pass the state visitation frequencies through a convolutional neural network to produce a latent variable which encodes the state visitations. We evaluate SOPHI in complex environments where reinforcement learning agents fail to learn interesting behaviors due to the sparsity of the task rewards. In these environments, learning effective policies is challenging because there exist many trajectories that don't find these sparse rewards. These include procedurally generated maps, pixel observations and sparse rewards, 3D navigation, and continuous actions. Our results show that SOPHI achieves better exploration performance, meaning higher state coverage in large environments. Importantly, we show that SOPHI enables agents to direct exploration efficiently towards the unvisited states. In this example, we artificially created some initial state visitation frequencies that indicate that all states have been visited many times, but the ones inside the red squares. Then we see that the same reinforcement learning agent, which starts in the yellow squares, is able to direct exploration towards the marked state. These results indicate that SOPHI enables agents to leverage the augmented information in the states, using the information in the visitation frequencies to modify their behaviors. Our results show that SOPHI is agnostic to the reinforcement learning algorithm, as we achieve better exploration, higher map coverage, and better downstream task performance with different algorithms, including PPO, SAC, DQN, and actor critic. Importantly, SOPHI provides orthogonal gains across multiple intrinsic rewards of different nature, including pseudo-counts and state entropy maximization. In conclusion, intrinsic rewards are key to solve challenging tasks and guide agents in absence of dense learning signals, but they are challenging to optimize because they're non-stationary. And in this work, we propose SOPHI, which makes intrinsic rewards stationary and achieves significant performance gains across many complex environments. I am looking forward to discussing our results further in Vienna for the next ICLR conference.